Hello, my name is Brad Greer, and this summer I did research in Amber Lab, investigating an accessible dynamic appendage module for increased control authority on legged robots. I worked with and would like to thank Min Dai, Xiaobin Sheng, and Dr. Aaron Ames for their time. So, legged robots are underactuated systems, and common ways of combating this property and increasing control authority are implementing low degree of freedom systems like flywheels, but these are typically highly limited, or more common nowadays, implementing high degree of freedom systems like 5 to 7 degree of freedom robotic arms that are capable but are not very dynamic. The basis for this design can be found in nature on several bipedal animals such as the ostrich or the pangolin. So the goals of this design were to create a link design that is robust to testing stresses, scalable to be able to take a form that can be tailored to any robotic platform, and the link itself also needs to be cheap and fabricated with accessible processes. In this project, I also wanted to realize a tail module with real hardware, as well as test it, and for the cables that drive the tail to be decentralized. Going into link design, all the parts of the link are either off the shelf or water jet. The 3 manual mill parts are on the motor test bed module. I brought the price down to below $20 per link, which is cheap for modern robotic hardware. And in general, I optimized each component for strength, weight, cost, and coefficient of friction for reducing the friction of the driven cables. Initial validation for the tail links was done with FEA, and factors of safety in every loading condition exceeded 2. Here's the CAD visualization of the driving module that was realized in hardware, and here's its driving architecture. The high-level controller is run on a PC and sends actuation commands to the motor drivers through a middle board. For non-experimental analysis, I developed a MATLAB tool that is fed a trajectory and solves for resulting forces and moments on the driving base, as well as cable actuation forces required to match the trajectory. The forces and animation displayed here correspond to this theoretical implementation of an appendage on the bipedal chassis platform. The future of this work, next I'd like to generalize the MATLAB tool here and the overall design process to make it implementable on arbitrary robotic platforms so that tails can be developed for any platform. And I'd want to continue working with the hardware that I've already developed and test its performance. Thank you.